Today we will study an important type of differential equation, that is homogeneous differential equations. Now viewers, before taking up the concept of homogeneous differential equation and the method to solve a homogeneous differential equation, let us first take the definition of homogeneous function. So what is an homogeneous function? A function f x comma y in x and y is said to be homogeneous function of degree n if it can be put in the form x raised to n f of y over x, or y raised to n f of x over y. Now let us take an example. Suppose we have a function, say f of x comma y, and the function is x cube plus say 3x square y plus y cube. Now let us take x cube common from this expression. So what we have x cube, then we have 1 plus 3 y over x plus y cube over x cube. Now this can be written as x cube 1 plus 3 times y over x, and this is plus y over x whole cube. Now see, this expression is some function of say g, or we can write g of y over x. So we have expressed this function f of x and y in terms of x cube times a function g of y over x. So here we have expressed it in this form, and here the value of n is 3, so the degree of this function is 3, and it is known as a homogeneous function, right? Now suppose instead of taking out x cube common out from this expression, if we take y cube common from this expression, then we'll have x cube over y cube plus 3 times we have x square. Here we have x square over y square, and then here we have 1, right? Okay, now this function f of x comma y can be written as y cube, and this is x over y whole cube, and then this can be written as 3 times x over y whole square, and then here we have 1. So this expression can be now written as y cube, and this expression is some function, say h of x over y. So here we have expressed this function f in this form y raised to n f of x over y, and here the degree is again 3. Therefore we can say that a function f of x comma y is in x and y is said to be homogeneous function of degree n if it can be put in the form x raised to n, and here now we can replace this f by g. So if f of x comma y is expressed in the form x raised to n times a function g of y over x, or y raised to n times some function h of x over y, and if any function which cannot be written in this form, then it is said to be not homogeneous, right? Let us take one more example. So here, suppose if we take a function, say x square plus y square, then obviously we can take x square common, so we have 1 plus y over x, and this is square, and we can write it like this. So this is x square times g of y over x, and here the value of n is 2, so the degree of f is 2, and it is a homogeneous function. But if instead of x square plus y square, if we had x square plus y, then we can easily see that we cannot take x square common, right? And this function cannot be written in this form, so this is not homogeneous function, right? So this is not a homogeneous function. Similarly, suppose we have a function, say f1 of x comma y is say x cube plus say 3x square y plus y raised to 4, then we see that this function cannot be expressed in this form or in this form. Why? Because see, here the degree of this term is 3, and here the degree of this term is 3, 2 plus 1 3, but here we have 4. So this is not a homogeneous function, right? So this is about the concept of homogeneous function. Now let us consider the definition of homogeneous differential equation. So an equation in x and y is said to be homogeneous if it can be put in the form dy by dx is equal to the function f1 divided by f2, and here f1 and f2 are both homogeneous. f1 and f2 are both homogeneous functions of same degree, right? Same degree. Okay. So now let us see the algorithm how to solve a homogeneous differential equation of this type, right? So here since the functions f1 and f2 are both homogeneous functions of same degree, and let us say the degree is n, right? So now using the definition of homogeneous function, will express f1 x comma y in the form x raised to n function g of y over x, and similarly we'll express f2 as x raised to n and some function say h of y over x, right? Okay, now here x raised to n and x raised to n get cancelled, so we are left with g of y over x, and here we have h of y over x. Now here we will make an important substitution, and the substitution is we'll put y over x is equal to v, where v is a function of x, right? So y is equal to vx. Now substituting y over x equal to v here, we get dy over dx is equal to g of v and h of v, right? Now this derivative of y with respect to x can now be expressed in terms of v and x. So here we have y equal to vx, so differentiating both sides with respect to x, so we get dy over dx equal to the derivative of v times x, and here v is a function of x, so here we'll apply the product rule. So this is dy over dx. First function derivative of x is 1, and then we have x and derivative of v with respect to x. So viewers, this is equal to v plus x dv over dx. So here we'll substitute this value, so we'll have v plus x dv over dx is equal to g of v and h of v. Now separating the variables, here we get x dv over dx is equal to g of v h of v minus v, which can be written as gv minus v times h of v divided by h of v, right? So x times dv over dx is equal to this expression, and see this entire expression is a function of v, right? And let us denote this expression as a function of v as say f of v, right? F of v. So viewers, we have now x times dv over dx is equal to f of v, and now separating the variables, dv over f of v is equal to dx over x, and now we can integrate both sides, and by making use of the techniques of integration, we can find the solution, right? And here we'll have the constant of integration. So viewers, this is how we will find the solution of a homogeneous differential equation of this type, where f1 and f2 are both homogeneous functions of same degree, right? So let us take another form of homogeneous differential equation. Now viewers, let us take the second type of homogeneous differential equation of first order, and here the equation is of the type dx over dy equal to f1 over f2, where f1 and f2 are both homogeneous functions of same degree, and let the degree be n, right? And in the previous discussion, we have seen the differential equation of the type dy over dx equal to f1 over f2, right? So here we have dx over dy, and here f1 and f2 are both homogeneous. So let us take that this function f1 and f2 are expressed in this form, right? That is y raised to n, and g of x over y, and this is divided by y raised to n, and h of say x over y, right? So in the previous equation, where we have taken dy over dx, then f1 and f2 were expressible in this form. Now in the case of dx over dy, let us take that f1 and f2 are expressible in this form, that is y raised to n h of x over y. So here we have g of x over y, and here we have h of x over y. Now these two terms get cancelled, so we have g of x over y, here h of x over y. Now as we have done in the previous discussion, let us put x over y equal to v, where v is a function of y, right? In the previous equation, the variable v was a function of x, but here the variable v is a function of y. So x can be taken as vy. Now this equation now reduces to for dx over dy, we can write the value of dx over dy by differentiating this expression with respect to y. So this is dx over dy. Here we have d over dy of vy, and here we'll apply the product rule. So this is v, the derivative of y is 1, and then we have y and the derivative of v with respect to y. So dx over dy is equal to v plus y times dv over dy. Now writing this value here, we have v plus y times dv over dy is equal to g of v divided by h of v. Taking this v to the right hand side, we have y dv over dy is equal to g of v divided by h of v minus v, and this can be written as g of v minus v times h of v divided by h of v. And separating the variables, now see this whole expression is a function of v, so let us take this as f of v. So we have y times dv over dy, and now separating the variables, we have dv over f of v is equal to dy over y, and now integrating both sides, we have here the constant of integration. So now integrating these expressions by making use of the techniques of integration, we can find the solution of this equation, right? And finally, when we are complete with the integration process, we'll again substitute the value of v as x over y in order to get the solution in the form of x and y. So viewers, this was all about the two types of differential equations. The first one was dy over dx equal to f1 x comma y, this is and f2 x comma y, right? And the second one is dx over dy equal to f1 x comma y divided by f2 x comma y. And now let us solve some problems. Now viewers, let us take this simple problem. Here we have to solve this equation, that is dy over dx is equal to y minus x divided by y plus x. Now here we see that dy over dx can be written as c, this is f1 and this is f2, and let us take x common out of the numerator. So we have x, and here we have y over x, and then we have minus 1, and again taking x common, we have y over x plus 1. So x and x get cancelled, So we have y over x minus 1 divided by y over x plus 1, right? So here we see that this is a homogeneous function of degree 1, and here this is also a homogeneous function of degree 1, right? Now let us substitute y over x is equal to v. So y is vx, and dy over dx can be written as v plus x dv over dx. And here always remember that when we substitute y over x is equal to v, then v is a function of x. Now let us substitute these values in equation 1. So dy by dx can be written as v plus x dv over dx is equal to v minus 1 divided by v plus 1, right? Now taking this v to this side, that is to the right hand side, so we have x dv over dx equal to v minus 1 v plus 1 minus v, and this can be simplified as v minus 1 multiplying this term by this, we have minus v square, and then we have minus v and divided by v plus 1. So v and v get cancelled, so we are left with minus 1 plus v square divided by 1 plus v, right? Now separating the variables, here we have 1 plus v divided by 1 plus v square dv is equal to minus dx over x, right? Separating the variables. So now if we integrate both sides with respect to the variables, here we have the variable v, here we have the variable x. So integrating both sides, c is the constant of integration. So here we have the integral 1 over 1 plus v square dv plus, and here we have v over 1 plus v square dv, and here we have minus log x, and this c can be written as log of some constant c1, right? Now this is 1 over 1 plus v square, so the integral is tan inverse of v, and for integrating this expression, here we multiply it by 2 and divide it by 2. So 2v is the derivative of 1 plus v square, so this is half log of 1 plus v square, and this is a log of c1 over x, right, by applying the properties of log. Now here again substituting the value of v as y over x, so we get tan inverse of y over x. Here we get half log 1 plus y square over x square, and this is log of c1 over x, and this is tan inverse y over x, and this can be written as half log x square plus y square, and taking x square by applying the property of log, we have minus half of log x square. So this is log c1 over x, right? So here we have applied the rule log m over n is equal to log m minus log n. Now taking this 2 to in front of log, by applying the property log m raised to a is equal to a log m. So we have tan inverse of y over x plus half log x square plus y square, and here we have 2 and 2 get cancelled, so we have minus log x, and taking minus okay, write it as minus log x, and here we have log c1 minus log x. Again writing log c1 over x as log c1 minus log x, because this log x and log x get cancelled. So viewers, we have tan inverse y over x plus half log x square plus y square is equal to log of c1, and log of c1 can again be written as some constant, say k. So this is the final solution of this differential equation. Now let us take this problem. This is a very important problem. Here we have this differential equation. So taking this term, we have actually 1 plus e raised to x by y dx plus e raised to x by y times 1 minus x over y dy equal to 0. Now taking this term to the right hand side, here we have the negative sign, and now simplifying it, taking dy to the denominator of dx here, so we have dx over dy is equal to minus e raised to x by y 1 minus x over y divided by 1 plus e raised to x by y. Now taking y to here, y ones are y, so we have y minus x divided by 1 plus e raised to x by y times y. Now viewers, from this differential equation, it is quite evident that here we have to substitute x over y is equal to v, where v is a function of y. So x is equal to vy, and dx over dy can be written as v plus y times dv over dy. Now substituting this value and this value in equation 1, so we have v plus y times dv over dy is equal to minus e raised to v. Here we have x over y is equal to v, so we have minus e raised to v, and then we have here y minus, for x we have vy, and then we have 1 plus e raised to v times y. Now taking y common, so this y and the y in the numerator get cancelled, so we have minus e raised to v 1 minus v divided by 1 plus e raised to v. Now taking this v to the right hand side, we have y times dv over dy is equal to minus e raised to v 1 minus v divided by 1 plus e raised to v minus v, and simplifying this expression, we have minus e raised to v plus v times e raised to v, and minus multiplying v by 1 plus e raised to v, so we have minus v minus v e raised to v, and divided by 1 plus e raised to v. Now this term and this term get cancelled, so viewers, we have y times dv over dy is equal to minus e raised to v minus v divided by 1 plus e raised to v. Now here separating the variables, we have 1 plus e raised to v divided by v plus e raised to v, because here we'll take the minus sign common, v plus e raised to v and divided by 1 plus e raised to v, and this is equal to minus dy over y. Right, now integrating both sides, here we have the constant of integration. Now we are see here the derivative of this v plus e raised to v is 1 plus e raised to v. So we have directly log of v plus e raised to v, and here we have minus log y, and this can be written as plus log of some constant, say k. Now this is log v plus e raised to v equal to log of k over y, right? Applying the property of log. So here we have both sides, we have log, so cancelling it out or taking the antilog, we have v plus e raised to v is equal to k over y, and this is y times multiplying this term by y here. So we have yv plus y times e raised to v is equal to k, and vy is equal to x. So here we have x plus y times e raised to x over y, because v is equal to x over y is equal to k. So viewers, this is the solution of this differential equation, right? So here we have solved this differential equation, which is a homogeneous differential equation. Now viewers, let us take this problem. Here we have to solve dy over dx minus y over x plus cosec y over x equal to 0, and here the boundary conditions are also given. So let us take these two terms to the right hand side. So we have y over x, and then we have minus cosec y over x. Now viewers, let us substitute here y over x is equal to v. So y is equal to vx, and here v is a function of x. So dy over dx is equal to v plus x dv over dx. Now substituting these values in equation 1, so we have v plus x dv over dx is equal to for y over x we have v, and then we have minus cosec v, right? Now this v and this v get cancelled, so we have x times dv over dx is equal to minus, this is minus cosec v, which can be written as minus 1 over sine v, right? Now separating the variables, we have sine v is equal to minus dx over x. Now integrating both sides, we have c as the constant of integration. So the integral of sine v is minus cos v, and here we have minus log x and plus c. Now here c is the constant of integration, and now substituting the value of v as y over x, so here we have minus cos y over x equal to minus log x plus c. So viewers, this is the general solution of this differential equation, and now we are given the initial conditions as y is equal to 0 and x equal to 1. So substituting these values here, we have minus cos 0 over 1, that is minus log of 1 plus c, and this is minus cos 0, and log 1 is 0, so we have 0 here, and plus c, and cos 0 is 1, so we have minus 1 is equal to c. So the value of c is minus 1. Substituting it here, we have cos minus cos y over x is equal to minus log x, and here we have plus minus 1, because the value of c is minus 1. Multiplying throughout by minus 1, we have cos y over x is equal to log x plus 1, and 1 can be written as log e, and this is log m plus log n. So this is log x times e, right? So here we have applied log m plus log n is equal to log m times n, right? So this is the particular solution of this differential equation, that is cosine of y over x is equal to log of ex.